Imagine living with diabetes. You have to prick your finger multiple times a day just to monitor your blood sugar levels. It's painful, inconvenient, and let's be honest, no one wants to live like that forever. Now, what if we can design a system that can predict hyperglycemia, which is high blood sugar, without drawing a single drop of blood, using nothing but your heartbeat and your pulse? Presenting a non-invasive AI-powered solution using ECG and PPG signals to detect hyperglycemia. In this video, I'll take you through the entire project from the core idea to the code, even the challenges that we faced and where this technology could go next. So let's start by understanding the problem that we're trying to solve here. Hyperglycemia is a condition where your blood sugar levels are higher than normal. So for someone with diabetes, this can be incredibly dangerous because if not monitored properly, hyperglycemia can lead to cardiovascular problems, nerve damage, and even diabetic coma for that matter. But here's the problem. Current monitoring techniques are invasive. Think of finger pricking tests or continuous glucose monitors that require sensors inserted under your skin. They're effective, no doubt, but they're uncomfortable, expensive, and not always ideal for continuous tracking. So we just thought, what if we could use biosignals that wearable devices like smartwatches already collect? Signals like ECG, which measures your heart's electrical activity, and PPG, which measures your pulse and blood flow. These are non-invasive and widely available. So that's the project, a completely non-invasive approach towards hyperglycemia prediction using these signals. So after completing the entire planning phase, we dove into the research. We found out some really exciting work. Studies had already shown that blood sugar levels impact heart rate variability and respiratory signals. Some researchers used ECG and accelerometer data to detect blood sugar fluctuations with decent accuracy. But most of these approaches were missing something. Either they focused only on signal, say ECG, or they used very small data sets, or didn't focus much on visualization part. We also noticed a lack of timestamp alignment in most of them. For example, the time when glucose was measured versus the time when ECG was recorded wasn't always matched. This leads to major prediction errors. So we decided to address this. Our solution integrates synchronized ECG and PPG signals with timestamped aligned glucose readings and uses a deep learning model to learn the subtle patterns that indicate hyperglycemia. Now let's talk about data, because without good data, there's no good AI. We collaborated with a healthcare startup called Scanbo, who provided us with a data set consisting of ECG, PPG, and blood glucose values for over 130 patients. These weren't just random signals either, they were synchronized. For each subject, we had the time when the ECG was recorded, when the PPG was taken, and when the blood sugar reading was noted. The human body is an intricate and highly responsive system. Among its many subsystems, the cardiovascular and autonomic nervous systems are particularly reflective of metabolic changes. The changes can be hyperglycemia, for that matter, a condition where blood sugar levels are elevated. And by understanding how glucose impacts biological systems and how those changes affect biosignals, like ECG, which is electrocardiogram, and PPG, which is photoplethysmogram, we can unlock new and non-invasive ways of diagnosing and monitoring disease. Overall, this project explores precisely that link, leveraging physiological signal data to detect hyperglycemia using deep learning. So let's talk about glucose for that matter. Glucose is the primary energy source for all cells in the body. It is delivered to tissues through the main bloodstream and absorbed via insulin-mediated mechanisms. So in healthy individuals, insulin helps transport glucose from the blood into cells, maintaining normal fasting glucose levels between around 70 to 100. But after meals, glucose levels rise temporarily and are managed by a coordinated hormonal response. So for accurate prediction, average blood glucose is considered to be far superior than just taking the high blood sugar levels or even the lowest blood sugar levels. However, in individuals with impaired insulin production, which is type 1 diabetes or type 2 diabetes, this regulation fails. The result is sustained high blood glucose levels, which is hyperglycemia, and chronic hyperglycemia can damage the endothelial lining of blood vessels, impair nerve function, and lead to cardiovascular diseases, retinopathy, neuropathy, and other such problems. The autonomic nervous system, which is also called as ANS, controls involuntary physiological functions like heart rate, blood pressure, respiration, and digestion. It has two branches, the sympathetic nervous system SNS and the parasympathetic nervous system, which is PNS. So the SNS stimulates fight or flight responses in the body, whereas the PNS, it promotes rest and digest functions. Hyperglycemia disrupts the balance between these two branches. Studies have shown that even moderate elevations in blood glucose can cause sympathetic overreactivity and parasympathetic withdrawal. And this imbalance manifests in cardiovascular control, which alters the heart rate variability, as discussed earlier, causing arrhythmic patterns and influencing respiration patterns as well. So, this autonomic dysfunction is a key reason why signals like ECG and PPG are reflective of metabolic changes and serve as effective markers for glucose related abnormalities. Let's talk about ECG. So, the ECG is a graphical recording of the heart's electrical activity. It is composed of the P wave, the QRS complex, and the T wave, which represents the electrical depolarization and repolarization of the atria and the ventricles, respectively. So hyperglycemia affects the ECG in many ways. So I think the first one we need to focus on is the altered heart rate variability, which is called as HRV. So HRV is the variation in time between two successive heartbeats. A healthy ANS maintains high HRV, and hyperglycemia reduces HRV by affecting the vagal tone and sympathetic drive. So this change in visible in the ECGs RR intervals. RR intervals are nothing but just time between two consecutive heartbeats, which become more uniform or erratic depending on the nature of the ANS disruption. Next thing is QT interval prolongation. So in hyperglycemia states, the QT interval, which represents ventricular depolarization and the repolarization, can be prolonged. This may predispose the individual to ventricular arrhythmias, and especially in diabetic patients. The third one is increased resting heart rate. So, due to sympathetic dominance, a person experiencing hyperglycemia may exhibit a higher than normal baseline heart rate, which can be consistently observed across ECG traces. So, by analyzing RR intervals, HRV, and the frequency and amplitude of ECG waves, I think we can gain valuable insights into the metabolic condition of the patient. This is also supported by all the many research papers, I would say, from the research survey that we conducted. Almost all papers have proved the fact, or perhaps stated the fact, that HRV and RR intervals are, one of the main indications of variations in sugar levels. So let's talk about PPG now. While ECG focuses on the electrical behavior of the heart, PPG captures the mechanical aspect of cardiovascular health. So specifically, the volume change in blood vessels over time. So it works by shining a light, usually infrared or green, doesn't matter, into the skin and detecting how much is absorbed versus how much is reflected. So when the heart pumps blood, more blood enters capillaries, changing the optical properties. So these fluctuations create the PPG waveform. PPG is particularly useful in hyperglycemia detection for many reasons. I think first is reduced peripheral perfusion. Chronic hyperglycemia leads to microvascular damage, reducing blood flow and other sorts of things. So this affects the amplitude and smoothness of the PPG waveform. Next is increased atrial stiffness. So high blood sugar levels promote the formation of what we call advanced glycation end products, which is AGEs, which stiffen blood vessels and reduce their elasticity. So as a result, pulse wave velocity increases and notches are being formed in the PPG, which disappear or shift, which affects many factors in the PPG. Next is changes in oxygen saturation. So through indirectly poor glucose regulation, this can impair oxygen delivery, especially in patients with diabetic complications. So SpO2 measurements derived from dual wavelength PPG can help identify this imbalance. So by extracting parameters like peak to peak intervals or respiratory rates and other things, I think in the PPG waveform we are able to infer systemic effects on glucose dysregulation. So let's understand why this approach works. So at the core of this project is the biological correlation between glucose levels and cardiovascular, or you can say autonomic physiology. So glucose doesn't act in isolation. It affects cells, tissues, vascular structure, and neural control. So these changes cascade into both electrical and mechanical signals captured by ECG and PPG. So electrical abnormalities due to altered autonomic control are captured through the PPG, and mechanical and vascular changes such as stiffness or perfusion are evident in PPG. So together, I think these signals, these two signals give us a comprehensive picture of an individual's physiological state. Moreover, since these signals are already captured by wearable devices, using them for non invasive hyperglycemia detection is both practical as well as scalable. Let's focus on the overall functioning of the human heart. Um, we'll keep it short. So, the human heart is an extraordinary organ. It's essential, it's efficient, and elegant in design as well. So, roughly the size of a clenched fist, this muscular organ beats around 100,000 times a day, pumping nearly 7,500 liters of blood through an intricate network of blood vessels. And its fundamental role is to maintain the continuous circulation of the blood, ensuring that oxygen, nutrients, and other hormones are, and as well as waste products for that matter, are transported to and from the tissues efficiently. So let's look at the functioning of this biological marvel in depth, from its structure and chambers to the electrical conduction systems, valves, hemodynamics, and how each beat is coordinated with remarkable precision. The heart is located slightly left of the midline in the thoracic cavity. It's protected by the ribcage and enclosed in sac called the pericardium. It has four chambers: the right atrium and the right ventricle on the right side, and the left atrium and the left ventricle on the left side. These chambers are separated by partitions: the interatrial septum and the interventricular septum. The right side of the blood handles deoxygenated blood, while the left side manages oxygenated blood. This separation allows the heart to simultaneously support pulmonary circulation, which deals with lungs, and systemic circulation, which deals with the entire body. The circulation of the blood follows a fixed one-way path through the heart. So, the first is deoxygenated blood returns from the body via the superior and inferior vena cava into the right atrium. When the right atrium contracts, it pushes the blood through the tricuspid valve into the right ventricle. The right ventricle then contracts, sending blood through the pulmonary valve into the pulmonary artery, which carries it to the lungs. In the lungs, carbon dioxide is exchanged for oxygen. The now oxygenated rich blood returns via the pulmonary veins into the left atrium. The left atrium contracts, pushing blood through the mitral valve into the left ventricle, and the left ventricle, which is the most muscular chamber, contracts and ejects blood through the aortic valve into the aorta, delivering oxygenated blood to the entire body. This two circuit system ensures that deoxygenated blood is routed to the lungs for oxygenation, while oxygenated rich blood is delivered to the organs and the tissues. The sequence of events that occurs from the beginning of one heartbeat to the next is called the cardiac cycle. It consists of three major phases. One is the atrial systole. The atria contracts, forcing blood into the ventricles. Next is the ventricular systole, where the ventricles contract, ejecting blood into the pulmonary artery and the aorta. And the third is diastole, where all chambers relax and the heart fills passively with blood. So the cardiac cycle duration is roughly around 0.8 seconds at a resting heart rate of 75 bpm. It is tightly regulated by electrical impulses and pressure gradients within the heart. Unlike skeletal muscles, the heart beats on its own, thanks to the intrinsic conduction system composed of autorhythmic cells. The heart's pacemaker is the sinoatrial node, which is called as SA node, located in the right atrium. So here's how the electrical conduction works. SA node initiates the impulse, around 70 to 100 impulses per minute. It causes the atria to contract. Then the AV node, which is atrioventricular node, it delays the signal slightly by 0.1 seconds, allowing the ventricular's time to fill with blood. Then comes the bundle of His. Bundle of His transmits impulses from the AV node down to the interventricular septum. Right and the left bundle branches, they carry impulses to the right and the left ventricles. Purkinje fibers distribute the impulse through the ventricular myocardium, causing powerful contractions. So this conduction pattern ensures that atria contracts first, followed by ventricles, allowing efficient blood ejection and refill. So the heart contains four valves, each playing a critical role in preventing backflow. One is the tricuspid valve between the right atrium and the right ventricle. We have the pulmonary valve between the right ventricle and the pulmonary artery. We have the mitral or the bicuspid valve between left atrium and the left ventricle. And we have the aortic valve between the left ventricle and the aorta. So these valves open and close in response to the pressure chambers within the heart chambers. So when the pressure behind a valve exceeds the pressure in front, the valve opens, otherwise it closes. So malfunctioning valves can lead to serious conditions such as leakages and even narrowing of the valves. So the closing of valves produces the characteristic heart sounds. So we have the lub and the dub. So the closure of the mitral or the bicuspid valve and the tricuspid valves produces a lub sound, and the closure of the aortic and pulmonary valves produces the dub sound. The pressure exerted by blood on the walls of arteries is known as blood pressure. So it has two components. One is the systolic pressure and the other is diastolic pressure. So the pressure during ventricular contraction is called as systolic pressure, and the pressure during the ventricular relaxation is called diastolic pressure. This rhythmic pressure gradient drives blood flow throughout the body. The atrial pulse is the direct result of ventricular systole, felt most clearly at peripheral points like the wrist or the neck. The heart muscles, also called as myocardium, needs oxygen-rich blood to function. It receives this via the coronary arteries, which branch off the base of the aorta. So during diastole, blood flows into the coronary arteries and nourishes the myocardium. Any obstruction, such as uh, atherosclerosis or anything, can reduce the supply and result in ischemia, potentially causing a heart attack, or also called as myocardial infarction. So regulation of heart rate is important, and we know heart rate is not static. It changes based on signals from the autonomic nervous system. So sympathetic stimulation is where heart rate increases, and parasympathetic stimulation is where the heart rate decreases. Other factors can also influence the heart rate, which are hormones, blood pressure, electrolyte balance, or other such factors. Okay. So the heart doesn't work in isolation. As I said earlier, it is a part of the intricate cardiovascular system, which is integrated with the respiratory, renal, nervous, and endocrine system. So its ability to adapt instantly to physical and physiological stimuli is vital for survival. So why have we used deep learning here? It's the first question which pops up. So traditional machine learning algorithms like SVM, decision trees, or KNN, they often rely on manually engineered features. While they work well for structured data, they struggle where patterns are deeply embedded into a noisy, high dimensional, or temporal data like biosignals. So deep learning, specifically fully connected feed-forward neural networks, are ideal for capturing complex nonlinear correlations between physiological variables and glucose levels. When paired with good feature engineering and pre-processing, these models can detect subtle biomarkers or of disease invisible to the human eye or classical algorithms. So what are we feeding the model? So this project works with synchronized data set. I've been emphasizing more on the word synchronized because that is something we are closely focusing on. The ECG features like RR intervals, HRV, and the heart rate. PPG features such as oxygen saturation, respiratory rate, the glucose values, high, average, and current, and time alignment info. Very important. The time difference between glucose reading and the signal capture. So after feature extraction, we build a structured data set uh, with 10 numerical features per record. The output label is binary. So 1 means hyperglycemia is detected, and 0 means that normal glucose state. So we've used augmentation here. We had a core data set of 132 patients with timestamp synchronized ECG and PPG and glucose levels. So we've used augmentation by introducing slight noise per row, so that one row transforms into 10 different rows. So that's how we've augmented the entire data set to achieve multiplication. So next comes is pre-processing, which is preparing data for training. So to ensure consistency across features, we have used standard scaler from scikit-learn. Each feature is transformed to zero mean and unit variance. Next is stratified split, which is an 80 to 20 train test split is used while maintaining class balance, which is important for imbalanced data sets. And outlier handling was minimal because of domain knowledge. Extreme RR intervals of HRV can represent real metabolic dysfunctions. We chose not to aggressively remove or impute those values because respecting the physiological diversity in the data. So we've tried to avoid removing it all. Let's focus on model architecture now. So the architecture was built using TensorFlow and Keras. So it is a feed-forward neural network composed of dense, fully connected layers with activation, normalization, and regularization. So here's a detailed layer structure. You have the input layer, which is 10 neurons, one for each feature. Next is the first hidden layer, which is 128 neurons with ReLU activation, with patch normalization, and with a dropout rate of zero point 0.2. The second hidden layer is again same ReLU activation, batch normalization with a dropout of zero point 0.2, but it has 64 neurons instead of 128. Third hidden layer has 32 neurons with just ReLU activation, and then finally we have the output layer, which is one neuron, and the output is produced using a sigmoid activation, which outputs a probability. So if the probability value exceeds zero point 0.5, so the user is classified to be hyperglycemic, and if it is less than zero point 0.5, the user is classified to be as non-hyperglycemic. So this architecture offers a balance between complexity and interpretability. So the dropout layer ensures regularization, while batch normalization accelerates and stabilizes learning. Since this is binary classification task, we have used the loss function. So loss function like binary cross entropy. So this is ideal when the output is binary and represented by a probability score from 0 to 1. And we've also used Adam optimizer. Okay, so Adam is adaptive, combining RMS prop and momentum. It adjusts the learning rate automatically, making it effectively for non-stationary objectives like biosignal metrics such as accuracy, precision, recall, F1 score, and the ROC and AOC to be produced effectively. Next is the training strategy and parameters. So the training was conducted with the following hyperparameters. We have kept the epochs to be 100. The batch size is 30. We've used early stopping, where the patient's value is 5 and the mode is min. We've also used a model checkpoint to save the model with the best validation accuracy. So the training and validation loss curves were plotted to ensure convergence and detect overfitting, and the training process stabilized within around 50 to 60 epochs in most runs. So how well did it work? So once trained, the model was evaluated on the test set. These are the key metrics used. So we've used confusion matrix, which helps visualize the number of true positives, false positives, and so on. We've used accuracy, which is the overall correctness of the predictions. We've used precision. Out of the predicted positives, how many are truly positive? Okay, so the correct predictions we've used. We've also used recall. So recall is like out of actual positives, how many were detected. We've used F1 score, which is the harmonic mean of precision and recall. We've also used ROC curve, which shows true positive rate versus false positive rate. And we've also used AUC. So we've got an AUC of 0.9, which was consistently achieved, which is a good result. So these results confirm that the model performs well in detecting hyperglycemia conditions from physiological features alone. So, in summary, I can say that we have collected a rich biosignal data set. We have engineered 10 vital features from ECG and PPG. We've built a robust neural network. We have trained and validated the model with proper regularization. We have deployed the system in a simple CLI interface. We have not. Um, the future scope of this project is to actually link with physical devices like smartwatches and etc. We can link with the front end. We've already done that using Fast API, but I think the wiser future scope would be to actually integrate with wearable devices. So this project proves that deep learning, when applied thoughtfully and paired with biological insights, can transform how we approach disease detection and management. You know, it's not just about technology; it's about building smarter healthcare systems, one signal at a time.